So good morning and welcome back to the course on classics in total synthesis part 1. So in the last lecture we talked about synthetic utility of radical cyclization in total synthesis of triquinanes, and where we talked about synthesis of two linear triquinanes, namely hirsutene and capnellene. These two were reported by Dennis Curran. And today we will continue our discussion on the applications of radical cyclization to two more triquinanes. One is an angular triquinane, other one is a propylene type. Okay. So the first one, the angular triquinane, which we will talk about today, is called Silphiperfolene. So this we already discussed via different method. Here what Curran has done is, if you look at the linear synthesis, where he has made a cyclopentene first, then he tried to have a side chain. He tried to have a side chain with a radical, and that will undergo 2,5-exo radical cyclization. So for this angular triquinane, again he wants to have only one 5-member ring, that is cyclopentene. Only the position of the two side chain differs. So if you look at the left hand side, it remains same. Okay. However, this side chain comes to here. Okay. So now if you look at this carefully, the 5-exo radical cyclization onto this double bond followed by another 5-exo radical cyclization will give you the angular triquinane. So this was the key strategy which he wanted to use in the synthesis of Silphiperfolene. Okay, let us see his retrosynthesis, and his idea is to have this vinyl bromide. This vinyl bromide should in principle undergo two successive 5-exo trig radical cyclization, whereas in the case of capnellene and hirsutene, which are linear angular triquinanes, he has used a 5-exo trig followed by 5-exo dig cyclization. Here it is two consecutive 5-exo trig cyclization. So this can be obtained from this particular cyclopentenone. So if you look at this carefully, first you can do two alkylation. Okay, one with methyl, the other one with this allyl halide, substituted allyl halide, then followed by the Grignard addition of 4-carbon unit onto this ketone, and hydrolysis will give this precursor. Okay. So the synthesis actually started with 3-ethoxycyclopentenone, which is very easy to make from cyclopentane 1,3-dione by treatment with ethanol and HCl. One can prepare this in large quantity. Now you do the alkylation first with methyl iodide, so you can introduce a methyl group at alpha carbon. Then again another alkylation with this substituted allyl bromide. So you could introduce two alkyl groups alpha to the carbonate. Okay. Now what you need is, you need to add a Grignard reagent. So the Grignard reagent is made from bromobutene. So the butynyl magnesium bromide was added to this ketone in a 1:2 fashion to get this allylic tertiary alcohol. Now this upon protonation, okay, once you protonate, you get this positive charge. Now the lone pair on this ethoxy group will come and then pushes this water molecule out. So you get the corresponding cyclopentenone. So this is the key precursor for the radical cyclization. So he took this compound, and one problem with this is the Michael acceptor. Okay. If you do a radical cyclization, first 5-exo trig radical cyclization will work. However, the second exo radical cyclization may not work. So that is why it is better to protect the carbonyl group. So the carbonyl group was protected as ethylene ketol by treating with ethylene glycol and acid. So then he carried out the key tandem radical cyclization. So the tandem radical cyclization worked well to give a mixture of two diastereomers. So this is the required isomer, but he also got the unwanted isomer in the ratio 3:1 in favor of the required isomer. Okay. So now what is required is you have to remove the ketol as well as remove the ketone. So the ketol was removed using treatment with acid, and the keto group was removed using Wolff-Kishner reduction. So that's how you could complete the total synthesis of Silphiperfolene. That the epimer also was made, where the ketol was removed and Wolff-Kishner reduction gave the corresponding Silphiperfolene. So in summary, if you look at this synthesis, Dennis Curran, who reported this synthesis in 1987, started with the cyclopentane 1,3-dione and used, like in the case of hirsutene as well as in capnalin, he used the tandem 5-exoteric radical cyclization to accomplish the total synthesis of Silphiperfolene. Overall, it took about 7 linear steps with a yield of 6.4%. So now from linear to angular we will go to propylene triquinanes. How propylene triquinanes can be synthesized using radical cyclization. So these are some of the propylene triquinanes, and the basic one is called modhephene, and there are some oxygenated modhephenes, 13-acetoxy modhephene, modhephene epoxide and polycarol. So this modhephene, first let us look at the modhephene. So you can call this as 3,3 propylene system. Okay, 3 carbon, 3 carbon, 3 carbon, all 3 carbon atoms are joined together. Okay, so that's why this is called 3,3,3 propylene system, and it was isolated from a goldenrod plant, and which was well known for its toxicity to cattle and sheep. And from the synthetic point of view, particularly from Dennis Curran's radical cyclization strategy point of view, he wanted to extend the same tandem radical cyclization. However, in this synthesis he faced quite a bit of problems. One, there are 3 contiguous quaternary center in modhephene, 1, 2 and 3. There are 3 contiguous quaternary centers. So it is not that easy to form 3 contiguous quaternary centers using tandem radical cyclization. This is a big challenge. Then you also have equal number of chiral centers, 1, 2, 3. 3 chiral centers are there. Okay, and particularly the chiral center with a methyl group, that is not that easy to fix. And the molecular architecture of modhephene is such a way that it does not allow the tandem radical cyclization to take place. So he has to do stepwise radical cyclization to achieve the total synthesis of modhephene. So let us see how he achieved the total synthesis of modhephene. So he thought about 4 different strategies. Okay, so let us not go into the details of how these 4 different strategies he wanted to use. He wanted to make first without this methyl group. So to check his strategy, so that is synthesis of des-methyl modhephene. So he started with cyclohexane 1,3-dione, and then if you treat with NBS, you can introduce the bromine at this carbon. Then you treat with methanol PTSA, so that will form the corresponding enol ether. So once you have this enol ether, then again you add this 4-butynyl magnesium bromide, what we have done for the synthesis of Silphiperfolene, followed by hydrolysis, you get the 3 homoallyl 2-bromo-cyclopentenone, 3 homoallyl 2-bromo-cyclopentenone. So now you reduce the enone with sodium borohydride cerium chloride under Luche reduction condition to get the corresponding allylic alcohol. So once you have this allylic alcohol, then treat with isobutyric anhydride. Okay. So when you treat with isobutyric anhydride, it forms the corresponding ester. The idea is once you have this ester, he wanted to carry out a Claisen rearrangement, intramolecular Claisen rearrangement. So for that he has to treat with LDA and TMS chloride, which in situ generate this enol TMS followed by Claisen rearrangement, island ester Claisen rearrangement to give this carboxylic acid. Okay. So now if you see, you have that dimethyl group, it's a quaternary carbon, and there is another quaternary carbon. So two quaternary carbons are made. Now what you need to do is to introduce the third quaternary carbon followed by cyclisation. So the carboxylic acid was esterified with the diazomethane to get the corresponding ester. Then he tried to cyclize this, okay, using radical cyclisation. You treat with tributyltin hydride and AABN. So here when you want to do radical cyclisation, you can use stoichiometric amount of tributyltin hydride and catalytic amount of AABN, or one can also use catalytic amount of tributyltin hydride, catalytic amount of AABN, but stoichiometric amount of sodium cyanoboride. So what does it mean? That is, the tributyl tin halide which is formed can be further reduced with sodium cyanoboride or sodium borohydride. So that is how one can use tributyl tin in catalytic amount. Okay. So now this reaction works well, as you can see here, 3:1 ratio of the cyclized product and then simple reduced product. And here the stereochemistry, what he got was 5:1 in ratio where the required isomer alpha is the major isomer. Okay. So successfully he could carry out the first radical cyclization. Okay, successfully he could carry out the first radical cyclization. Now what he has to do is he has to connect here these two carbon, connect these two carbon to form the third ring. Okay. So for that what he did, he reduced the ester to alcohol. So once you have the alcohol, you oxidize to aldehyde, and then treatment with triphenylphosphine and CBr4 will give you corresponding dibromoalkene. Okay. So he wanted to use this dibromoalkene as the radical precursor. Okay. So you can see you have two bromines, okay, and if it cyclizes here, so that will give you the corresponding modhephene. So when he did this reaction with 1.1 equivalent of tributyl tin hydride and AABN. So between these two bromides, we should know which one will form radical first. Obviously, so this is more exposed or least hindered, isn't it? So that will form the radical quickly. So that radical was formed, and if this radical is formed, then this cannot cyclize. So what it will happen? It will take up the hydrogen and it will simply reduce. And this also does not isomerize. Okay. This does not isomerize. So he thought this will isomerize to the trans compound, and the trans compound can undergo the 5-exo trig radical cyclization. But the isomerization did not take place. With 1.1 equivalent of tributyl tin hydride and AABN, only the less hindered bromine was replaced. Okay, that only was reductively removed. Okay, the exchange did not take place. So what he thought? So instead of using 1.1 equivalent of tributyl tin hydride, he thought he will use catalytic amount of tributyl tin hydride and excess sodium cyanoborohydride. Okay, and here the idea is, first anyhow only this bromide is reduced. Okay, so let it reduce. Afterwards, if you add excess sodium cyanoborohydride, which will in turn generate more tributyl tin hydride, then this bromine will be replaced by radical, and that can undergo cyclization. So with this he tried this reaction, and as expected, first the least hindered bromide was reductively removed, then followed by further heating under the same condition, the trans radical was formed and which underwent further cyclization to give des-methyl modhephene. So if you look at the modhephene structure, you need one extra methyl group here. Okay. So based on this, he wanted to extend the same strategy to the synthesis of modhephene. So for that, he started with this trimethyl tin derivative. Okay. This trimethyl tin derivative, what he did, if you treat with LDA, you can generate anion here. Okay. That anion will come like this and then it will attack this carbon, that is a primary halide. So alkylation will take place at the primary halide and the secondary halide will not be affected. So that will give you this derivative. His idea was, now if you can generate radical here, okay, that radical can undergo cyclization 5XO, and when it comes back, the trimethyl tin radical will come out. That way you have the double bond still intact. So with this, he treated with tributyltin tin hydride in the presence of AABN. So he got exclusively this product. How did he get? The tributyltin tin hydride first generates the tributyltin tin radical, okay, and it exchanges with bromine. So you get the secondary radical. Okay. So when I talked about radical cyclization, the stereochemical outcome of radical cyclization, particularly for 5XO radical cyclization, can be done by drawing a chair-like conformation. So exactly, if you see this, we have drawn a chair-like conformation. So the first step is the addition of the radical to the double bond, 5XO trig. So that should give you this compound. Okay. I will leave it for few seconds so that now you can understand this. So this will undergo 5XO radical cyclization to give this radical. Now this radical will come like this and then eliminate the tributyl tin radical. So you can write like this. Yeah. Okay. So that is how this cyclization takes place, and the methyl group, which is alpha, it is because here the methyl group was put in equatorial position. So that is how the chair-like conformation will help in establishing the stereochemistry of the methyl group which is formed here. Okay. So once you have this bicyclic system, the next step is you have to convert this ester into a dimethyl group and then CH2. So for that, first you hydrolyze the ester to carboxylic acid and then treat with acid chloride, you get the corresponding acid chloride. So now what he did was he tried a Sakurai-like reaction where the allyl TMS, okay, the allyl TMS was treated with this acid chloride in the presence of titanium tetrachloride to add this bromo allyl group directly to the carbonyl group. So now if you look at this, so you have the vinyl bromide, which on treatment with tributyltin tin hydride should generate the radical, and that radical should add here to form the third 5-membered ring. Otherwise that will give the core structure of modhephene. So when you did this reaction, yes, the reaction worked well and then you could get the propylene structure. So now what is required is convert this carbonyl group. The carbonyl group should be converted into dimethyl group. Okay. So if you look at the radical cyclization, first the radical cyclization took place, followed by the migration of the double bond, internal double bond. Instead of external double bond, you get internal double bond. That is because you have a ketone after radical cyclization, because normally radical cyclization you do it at high temperature. So the double bond, exocyclic double bond, migrated to alpha beta unsaturated ketone. So what he did to introduce the two methyl groups, first he treated with methyl lithium to get the corresponding tertiary alcohol. These tertiary alcohols are known if you treat with titanium tetrachloride and dimethyl zinc, Okay, it is known, well known in the literature that tertiary alcohol can be converted into quaternary by treatment with titanium tetrachloride and dimethyl zinc. So basically, the Lewis acid will coordinate with OH to make it as a good leaving group, and dimethyl zinc will deliver the methyl group. One can also do the same thing by treating with dimethyl zinc titanium chloride in the presence of TMS bromide. Okay. So effectively what you are doing is you are converting the tertiary alcohol into quaternary. So this is what was the expected product, but what he got was another product that can be